Hey everyone, so what I want to do here is go through the 6 trials for the ramp extension lab. This is in the constant acceleration model that we've now discovered. So we're going to look at the cart rolling up and down the ramp here. We're going to create position time graphs, velocity time graphs, and acceleration time graphs, and motion maps for all these different trials. And from this we'll be able to see how the constant acceleration model is different from the constant velocity model. So this is going to be our setup. Our setup is a track inclined at an angle. We've got the motion sensor at the top end of the track plugged into our spark, and this cart will roll up and down the ramp. So each trial we're going to do what the worksheet tells us to do and go from there to see the position, velocity, and time graphs. Here's scenario 1, increasing speed in the positive direction. So as we can see here, the position was increasing as time went on. It was increasing in the positive direction, and we know that the slope of position time graphs should give us velocity. So let's look at the velocity graph. Here's the velocity increasing as time goes on. This is a constant slope this time in the positive direction. Let's look at acceleration. Here is the acceleration for that trial. The acceleration was a flat, constant line in the positive direction. So we have constant positive acceleration as it sped up down the ramp. Let's look at motion maps for scenario 1 to show you how I would draw velocity vectors, or velocity arrows, and acceleration arrows as we gain speed down the ramp. Here's the motion map for scenario 1. You got the cart rolling down the hill away from the sensor. So you can see that the dots would increase and get further and further apart every single second, which means that my velocity would be getting faster and faster and faster each second. Now they also want you to put an acceleration arrow on here as well to show what the direction of the acceleration is. One way you could do it is label that all of these are velocities, and then above or below show an acceleration. So the way I'll do it is I'll have the acceleration be red for you. So the acceleration from the first moment to the second moment is down the hill. The acceleration from the second moment to the third moment is down the hill. And the acceleration from the third to the fourth is down the hill. From our graph we saw that so my acceleration was nice and steady, so these accelerations are all even as I go down the hill. Now the way to show that my velocity is changing is show that this velocity is different than the next, from the next, and the next. So I can see that my velocities are getting faster as time goes on due to a nice constant acceleration down the hill. Here's scenario 2. So in this scenario, we started near the origin, and you can see that I was moving very quickly in the beginning. That slope was very, very steep. So I had a very high positive slope, but then it started to gradually decrease. So this is a decreasing slope as we head up to the top, which means our velocity started off very positive after I threw it, and gradually lost velocity as it headed to the top. So it eventually came to rest when I caught it. So acceleration the entire time here was a flat negative line. We were always having negative acceleration on the object as it was heading up the ramp in the positive direction. Here's the motion map for scenario 2. The box going up the hill as it slows down. So you can see the dots get far apart in the beginning and then start to get closer and closer as it slows down. So if I draw my velocity vectors, they are longer in the beginning and shorter at the end. Again, we want to label these all velocities, and then we want to include acceleration. Well, if you look at the acceleration graph, the acceleration was negative the entire trip. And I'll do the acceleration in red again. So the acceleration was negative as it started moving from the first second to the second, negative for the next moment, and negative for the next moment. That acceleration was constant the entire time, so the accelerations were all negative and constant, and the velocities were getting smaller and smaller as time went on. Okay, scenario 3. We're going to increase our speed in the negative direction, so I'm going to put the sensor at the bottom of the ramp now, and have the cart run down towards the sensor. So I do need to make sure I catch it. Alright, so for the position graph here, you can see I started off at 2 meters, and my slopes were very gradual in the beginning, and they started getting steeper and steeper as we got close to the end. I was accelerating towards the origin with this graph. The velocity graph here had a little hitch in the beginning, but the cart was initially sitting still, and we can see it started to gain speed as it went down the ramp, and we have a nice constant negative line here for our velocity. We're constantly gaining velocity in the negative direction. And what we end up seeing here for an acceleration graph is a flat, constant line in the negative acceleration range. So as we picked up speed, we had a negative acceleration and a negative increase in our velocity. We're going to do position, speed, and velocity graphs here for an object that's decreasing speed as it heads up the ramp. So this time, what we can see is that the position graph is a curved graph with the position starting far away from the origin and the slope being very negative in the beginning and gradually sloping to 0 as it stopped at the end. The velocity graph here you can see is a positive line with a constant slope from some negative velocity all the way until it reaches 0. And here's the acceleration graph for this one. It is a constant flat line around 1 meter per second squared for the entire trial. Constant line, +1. In scenario 5, I'm going to put the motion sensor at the bottom like it is, and we're going to give the cart a push up the ramp, and I'm going to catch it right before it comes back to the sensor. So here's the position time graph for scenario 5. You can see it started near the sensor. I was moving very quickly in the beginning, moving away from the sensor, flattened out near the top, and then I have an increasing negative slope on the way back. So that's what's going on with my position every single second. If we go and look at our velocity, here's our velocity for the whole scenario. Started off very positive at near 1.5. The velocity got lower and lower until about this moment here. Right around 5.3 seconds, we have 0 velocity, and then you can see my velocity keeps getting negative and more negative as it heads back to the sensor. With a velocity graph that looks like this, the slope of velocity turns into acceleration, which gives us an acceleration of this, a nice negative acceleration the entire time, slowing the cart down on the way up and speeding the cart up on the way back. I'm making a motion map for scenario 5. Scenario 6, same scenario again, but I'm going to put the motion sensor at a different spot. I'm going to put it at the top. So here you can see, in this, I was moving very quickly in the beginning. Around 14 seconds, I leveled out and stopped moving. And then, on the way back, increased speed as I headed back to the start position. Looking at velocity here, my velocity started off negative. My negative velocity got less and less as I approached the 14-second mark, and right at 14 seconds you can see I'm not moving. And then my velocity increased in the positive direction as I headed back towards the bottom. So we saw the velocity graph was a nice constant slope, constantly positive, which leads us to a positive acceleration here. A nice constant positive acceleration the entire trip on the way up and back for this ramp. So for each scenario, make sure you do a motion map, make sure you have the graphs of position, velocity, acceleration, and with your motion maps, make sure you include an acceleration arrow as well as velocity arrows.